Hey guys, time to finish up chapter 5 with 5.5. Make note that we will not be doing the last two sections of this chapter. So, let's talk a little bit about modeling using the power property and how to make predictions. So, a person wants to invest $7,000 in a bank account with a yearly interest rate of 6%. It's compounded annually, and they want to know when their balance will be $10,000. So we need to set up a function b for balance, and our balance is going to be in thousands of dollars in t years. So we're going to write an exponential function that looks like the function of t is equal to a times b to the t. And remember that we are going to invest 7,000. So our initial amount is going to be 7. And our multiplier is going to be 1.06 so that we include the previous balance plus add 6% interest for every t year. We talked about the idea of how you had to add 1 to percentage rates when we are increasing. So to find when the balance is equal to 10,000, we will set b equal to 10, and since we know our answer will be in thousands. We will say 10 is equal to the 7,000 we started with times 1.06 t to the t. We divide each side by 7. And then we have the log of 10/7 is equal to the log of 1.06 to the t. We see that that exponent is still inside the parentheses and in an exponent, or the variable is inside the parentheses and is an exponent. So it's important for us to use a power property to bring that in the front. So we have log of 10 divided by 7 equals t log 1.06. So we divide each side by the log of 1.06, and when we plug that into our calculator to the fourth place value, we get 6.1212. Now we can take a look at what this does in our graphing calculator. If you were to plug y1 and have our equation 7 times 1.06 to the x, and I inserted a picture here of a calculator screen. If you change the independent or the x value to be ask in your table setup, that will allow you to put in that exact value 6.1212 and it will give you the y value. So set this to ask and then you can use that and look at that. Y1 is equal to 10, which is $10,000. So to make a prediction, we can use the general form. The function of t is equal to a b to the t. We divide each side by the coefficient a, and next we take the log of each side and use the power property to solve for t. So let's look now at the power property and using our ability to estimate when something will double. So we have the function of t is equal to 291 times 1.079 to the t, and that can be used to model federal debt amounts. We want to know that when the federal debt will double. So if you look at 1960, the debt was 291. So that when we want that to double, we'll be wondering when the debt is equal to $582 billion. So we are substituting 582 for the function of t and then solving. So 582 will equal 291 times 1.079 raised to the t. We divide each side by 291. That was my husband walking by. So we have 2 is equal to 1.079 to the t, and we have the variable we're looking for in the exponent place, so we know we have to take the logarithm of both sides. We use the power property to bring the t to the front, and we divide each side by the log of 1.079, and t will be approximately 9.12. So what did we actually find? We found that when t, which was our time, is 9.12, that means that the federal debt was doubling every 9 years. We can also use this idea to find half-life problems. So the half-life of an element is about the amount of time it takes for the number of atoms to reduce by half. So we're going to take a look at some carbon dating elements of carbon 12 and carbon 14. Carbon-14 is a radioactive chemical, and after an animal or plant dies, its carbon-14 decays exponentially with a half-life of 5,730 years. However, carbon-12 remains constant. So scientists know that there's this ratio between carbon-14 and carbon-12 in all living organisms. So they can determine how long an organism lived by measuring the decreased ratio of carbon-14 and carbon-12. So we can use that. We can also use half-life to make an estimate of when something happened. So there was this violent volcanic eruption that happened, and as a result, it created a crater lake, which happens to be the deepest lake in the United States. Scientists found a charcoal sample of a tree that burned in this eruption from the volcano that caused the crater lake. When they found that, it only had 39.4% of carbon-14 remaining. So we want to know, when did Crater Lake form? So we are going to let P be the function of T, which is the percentage of carbon-14 that remains after T years in that piece of wood. And since the percentage is halved every 5,730 years, we will find the exponential equation in the form that you see there at the bottom. The function of T is equal to AB to the T. So when it started, when that fire happened, when that volcanic eruption happened, there was 100% of that carbon in that tree. And what remains is 39.4. So we are going to say that at the beginning of time, when T was 0, there was 100%. So we have that point where we know the beginning amount, A, is 100. And we can start the equation as a function of T is equal to 100 B raised to the T. When time was equal to 5,730, we know that there was half of the remaining, because that's the half-life. So we can substitute the coordinates of the point 5,730 years. There was 50% remaining, and we can now solve for B. So when we plug in those points that we just determined, we get 50 is equal to 100B to the 5,730. We divide each side by 100. And now we notice that if we take and raise each side to 1 over 5,730, B is equal to plus or minus 1/2 raised to 1 over 5,730, or approximately 0.9999. So the equation that we can use is the beginning amount, which was 100%, times the multiplier, 0.99, and they carried this out many place values to be accurate, 9879 raised to the T. Now, we were wondering, when is that equation going to be equal to 39.4? Because that's how much carbon-14 remained in that piece of wood. So as we solve for T, we are going to divide each side by 100. We're going to take the logarithm of each side. You guessed it, we're going to take the power property to lower T in front. Now we're going to divide by the log of 0.99879 to find that T is approximately 7697. So what does that mean? What did we just find? T was time. So Crater Lake and the sample was approximately 7,697 years old. I hope that helps you solve problems at 5.5, and I keep praying for you and your families to remain healthy and safe, both physically and mentally during these tough times. And I look forward to seeing you soon, and I miss all of you. Everybody have a great week. The next video will be up shortly. Bye-bye.